Good afternoon. This is Wenbo. I'm a PhD student in Department of Psychology at McGill University, Canada. It is a great pleasure to be back to Oslo. Today I'm going to talk about the effects of music tempo and spontaneous rates on pain perception. Previous research has demonstrated music's capability in reducing pain across a variety of contexts, including during surgical procedures, post-operative recovery, and in the management of chronic pain. This non-intrusive, low-cost intervention holds great promise in transforming the standard of care for patients experiencing pain. This effect, referred to as music-induced hypergeusia or sometimes analgesia, is theorized to occur through two mechanisms. First, music may serve as a distraction, diverting the participants' attention away from pain. Second, music can regulate emotion, arousal, and associated psychophysiological states to reduce pain perception. For example, studies have shown that self-selected, enjoyable music can significantly reduce ratings of both intensity and unpleasantness of pain. On the other hand, the structural property of music such as rhythm, tempo have also been shown to influence involuntary autonomic functions and emotional arousal. Though findings remain complex and at times contradictory, research generally suggests that fast tempos tend to evoke higher arousal, while slower tempos reduce arousal and promote a more relaxed psychophysiological state. Recently, a study demonstrated that sensory-motor synchronization, which is tapping along to the beats of music, can also reduce pain. However, the direct relationship between music tempo or any other structural elements of music and pain modulation remain underexplored. An additional important perspective is that humans demonstrate intrinsic individual differences in spontaneous rates, which manifest across behaviors like walking, speaking. In the absence of external rate cues, people show substantial yet consistent individual variations in spontaneous rates in music production. As you can read the figures in the left, follow-up studies revealed that musicians tend to drift toward their spontaneous rates when performing music, and synchronizes better with partners who have similar spontaneous rates. These findings suggest spontaneous rates represent each individual's most naturally efficient or optimal rhythmic frequency, and consistent with a tractor point of optimal energy. Therefore, in our study, we investigated the effect of music tempo as well as intrinsic frequencies on pain perception. We hypothesized that music presented at tempi close to an individual's spontaneous rate, SPR, will reduce pain perception more effectively than music at other tempi, following dynamical systems principles. We have 60 healthy participants, with 20 musicians and 40 non-musicians. Participants were exposed to unfamiliar 2.5-minute musical excerpt purchased from a music royalty website. 20 excerpts were selected in a steady tempo and categorized as 4 styles: classical, dance, popular, and international. Each participant was assigned to one piece of music based on their preference of music style and their also spontaneous rate. Then we created 3 versions, one with tempo set to spontaneous rate, one set to spontaneous rate 15% faster, and one set to 15% slower. This design aims to create a big enough tempo differences between conditions even for non-musicians, and not to distort the stimulus when we do the tempo manipulation. We used a heated thermal to deliver and quantify pain. As you can see in the upper left, this device can quantify and deliver pain stimuli by generating heat. The baseline temperature is around 32 degrees, which is similar to our skin temperature. When we initiate a pain sequence, it will generate a target temperature such as 45 degrees, which will cause pain but won't physically damage participants' skin. In our design, the heat simulation was set to 40% of subjective pain threshold calculated from the pain calibration procedure, and we used an intermittent pain protocol, alternating target pain temperature and rest for a total of 2.5 minutes. In the experiment, we first let participants select a preferred music style. Then the individual's spontaneous rate was determined by tapping a familiar melody, Twinkle Twinkle Little Star, on a tapping pad at a comfortable, steady rate 3 times. We then calculate the mean intertap interval as the spontaneous rate. Afterward, we apply the standard pain calibration procedure as mentioned before, because everyone differs in perceiving pain. Finally, we had a within-subject design where all participants went through 4 conditions: pain without music, pain with music set to spontaneous rate, pain with music 15% faster than spontaneous rate, and pain with music 50% slower than spontaneous rate. The order was counterbalanced. As we expected, we observed substantial yet reliable individual differences in the intrinsic frequencies of participants as measured by spontaneous rates. As you can see in the figure, the SPR ranged from 250 milliseconds to over 700 milliseconds, with the slowest person's spontaneous rate around 3 times slower than the fastest person's. Moreover, there were no group differences in spontaneous rates between musicians and non-musicians. Secondly, as you can see, our study successfully replicated previous findings regarding the music and pain that the presence of music reduced pain. Most importantly, aligned with our hypothesis, we found that compared to the faster and slower conditions, when the music was set to the individual spontaneous rate, participants have a significant lowest pain level. This U-shaped pattern has a medium to large effect size. In comparison to other similar music and pain studies, this effect size can be considered one of the largest. However, we did not find any significant differences in music preference ratings across the 3 conditions. Hence, this phenomenon cannot be simply explained by participants preferring the music at their spontaneous rates. You may still be wondering if this effect is truly related to individual intrinsic frequencies, or due to the impact of other variables. For instance, if the SPR tempi are more closer to the original composition's tempi. Therefore, we ran correlation analysis between altered tempi and the pain ratings. The x-axis shows altered tempo in IOI, calculated as the original tempo minus the presentation tempo. The y-axis shows corresponding pain ratings. If our effect was due to the original composition's tempi being most optimized tempi, we would expect bigger alterations to correlate with higher pain levels. However, we saw no significant correlation between altered tempo and pain. This interpretation is further supported when we removed 25 participants whose spontaneous rates fell within one just noticeable difference of the original stimulus tempo. Even in this reduced subset, we still observed a similar U-shaped pattern with a comparable effect size, and we didn't find any interaction between the experimental conditions and style choices or specific music. Overall, this analysis provides concrete evidence that spontaneous rates rather than original composition tempi drove the pen reduction effect we observed. In summary, we firstly successfully replicate previous findings that the presence of music reduced perceived pain. And most importantly, we found that when music tempo matched to an individual's spontaneous rate can optimize pain reduction effects. Finally, we found that the original composition tempi, musical preferences, and style choices did not account for the effect of spontaneous rates on pain perception. Therefore, based on dynamical system principles and results from our experiment, we propose a new mechanism underlying music's pain reduction effects. Specifically, we suggest an individual's intrinsic frequency, as measured by spontaneous rate, represents their state of most energy efficiency. Hence, music matched to this spontaneous rate elicits most entrainment of individuals' endogenous regions, yielding optimized pain reduction effect. Last but not least, I would like to thank McGill University and the Natural Science and Engineering Research Council of Canada to fund my study, and also my supervisors, Drs. Caroline Palmer and Matthew Roy. We also thank our talented lab coordinators, RA, for their help with the experiment. Thank you.